Welcome back, everybody. What I'd like to talk about next is section 4.2, Homogeneous Constant Coefficient Differential Equations. In section 4.1, we talked about the structure of the solutions to the linear differential equations. Specifically, we looked at or talked about the homogeneous case, where the forcing function, the function on the right-hand side of the differential equation, is 0. In this section, we talk exclusively about that case, and even more specifically, we talk about the case where the coefficients to the derivatives or of the derivatives are constants. So the a sub n, the a sub n minus 1, all the way down to the a sub 0 are constant functions, or constant numbers, scalars. Okay, so how does the method work? So let's start with a specific example. Let's see here, example. Let's consider the differential equation y double prime minus y equals 0. And the idea is to solve the differential equation. Well, the method goes something like this. Look what happens if we solve for y double prime. If we solve for y double prime, we're looking for then a function or functions. We're looking for functions such that the second derivative of the function equals the function itself. What does this suggest? What kind of functions, when you take their derivatives or multiple derivatives, you get the function back? What this suggests is that the solution or solutions should involve the exponential function. So what this suggests is that our solution should look like something of the form e to a constant x, and we'll call the constant the Greek letter lambda, which is kind of standard. So the idea that the second derivative of the function equals itself suggests the exponential function is a solution, so we'll make that assumption. We'll assume that the solution is y equals e to some number x. Well, since this is going to be a solution, we should be able to substitute this solution into the differential equation and have it work. And that's how we're going to find the constant or constants lambda. So if we let y equal e to the lambda x, and if we're going to substitute this function into the differential equation, we're going to need a couple derivatives. So y prime equals, the derivative of e to the lambda x is e to the lambda x times by the chain rule lambda. So our first derivative is y prime equals lambda e to the lambda x. Okay, well, we need a second derivative, so let's take a second derivative. The second derivative then, again, using the chain rule, we're going to get another factor of lambda, so we get lambda squared e to the lambda x. And then we substitute this function into the differential equation. If we substitute into the differential equation, what we get is that y double prime minus y, the left-hand side of the differential equation, then equals lambda squared e to the lambda x minus e to the lambda x. And that needs to equal the right-hand side, which for this section, again, this is the section where we talk only about the homogeneous case. The right-hand side is going to equal 0. Well, we can solve this equation very easily by factoring out the greatest common factor of e to the lambda x, and then multiplying that by the remaining factor, lambda squared minus 1 equals 0. Okay? So let's solve this equation. Well, e to the lambda x is never equal to 0. So we don't have to worry about a contribution from to the solutions from the e to the lambda x part. However, lambda squared minus 1 equals 0 does have a solution. In fact, it has two solutions. It's a quadratic. Before we examine those two solutions, let's talk a little bit about terminology. This lambda squared minus 1 is called the auxiliary polynomial. This is called the auxiliary polynomial. Sometimes it's called the characteristic polynomial. Either term is just fine. Okay, and when we're identifying the auxiliary polynomial in writing, we refer to it as P of lambda. Okay, the equation where lambda squared minus 1 equals 0, this equation is called the auxiliary equation. So this is called the auxiliary equation. Okay, so in order to find the solution to our differential equation, or solutions to our differential equation, we need to solve the auxiliary equation, or the characteristic equation, if you will. Okay, so let's proceed. Let's move forward. Let's solve the auxiliary equation. Lambda squared minus 1. If lambda squared minus 1 equals 0, we can factor this equation into lambda minus 1 times lambda plus 1, since we're looking at the difference of squares. So it looks like two possible solutions. The only two possible solutions for lambda are lambda equals 1 and lambda equals negative 1. Okay, from this we see that then e to the 1x and e to the negative 1x are solutions. Remember, the original idea is that we were assuming that our solutions were of the form e to the lambda x. We were making the assumption initially that the solutions looked like e to the lambda x. Okay, and we found that the possible values for lambda were 1 and negative 1. So e to the 1x, that's a funny looking 1, and e to the minus 1x are solutions. Okay, all right. So remember what we talked about in the last section is that we were looking for a set of, in this case, two linear independent solutions. Two, because the order of the differential equation was 2. And once we had that set of two linear independent solutions, our theory guaranteed us the structure of our solution. So the set e to the x and e to the minus x, if that set is linearly independent, then this set forms a fundamental set of solutions for the differential equation. Now these two functions are linearly independent. E to the x and e to the negative x are not proportional to one another, so they are in fact linearly independent. And we know from our theory in vector spaces that if the dimension of the vector space is 2, which ours is, and we find two linearly independent vectors from the set, then we automatically have spanning. We automatically have a basis for the solution space to the differential equation. So we have in fact found a fundamental set of solutions. So this is a fundamental set of solutions. Okay. So our theory from last time then said that the general solution looks like y equals c1 e to the x plus c2 e to the negative x. Okay. So this is basically how the method works. What we're going to do for the remainder of this lecture is a couple of things. First we'd like to look at a way of skipping the idea of verifying that we have a fundamental set of solutions once we have the solutions to the auxiliary equation. We'd like to be able to go directly to the general solution rather than to have to identify the fundamental set as being a set of linearly independent vectors. And then what we'll do to finish off the lecture, which will take us a little bit of time, is to look at different cases depending on what specific types of solutions we do get from the auxiliary equation. So let's first see how we can maybe skip the initial step of identifying the solution as e to the lambda x. Okay, there must be a correlation between the original differential equation, y double prime minus y equals 0, and the auxiliary equation, lambda squared minus 1 equals 0. And it's pretty clear that there's a, oops, e not equal 1 equals 0. It's pretty clear that we kind of have a correspondence here. Look at the differential equation with coefficients written in. It looks like we have 1 y double prime minus 1 y equals 0, and 1 lambda squared minus 1 equals 0 for the auxiliary equation. This type of thing always happens. So our next thing is to skip the initial assumption. No, we're actually not going to skip the assumption, but skip the initial writing of the solution as y equals e to the lambda x, and substituting that into the differential equation to identify the auxiliary equation. We're going to go directly to the general case. So the general case says, consider the linear differential, homogeneous constant coefficient linear differential equation. Oh my goodness, that was one big chunk to chew. A sub n, nth derivative, a sub n minus 1, the a's are constants, remember, in our intersection, n minus first derivative, plus dot dot dot, all the way down to a sub 1 y prime plus a sub 0 y equals 0. Then the auxiliary polynomial p of lambda, then the p of lambda then is nothing more than a sub n lambda to the nth power. So notice that above here, right about here, let's do this, oops, above here, that didn't work out very well, let's do this again. Let's see. Well, it's not going to cooperate. We'll get fancy with colors later. Okay. Notice that in the differential equation we're looking at 1 y double prime, and in the corresponding auxiliary equation we have 1 lambda squared. So the order of derivative corresponds to the power of the lambda in the auxiliary polynomial. So continuing on, we have, change this back, we have plus a sub n minus 1 lambda to the n minus first power plus dot 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 all the way down to a sub 1 lambda plus a sub 0. Now notice there's no power of lambda on a sub 0. The order of derivative, if you will, in this last term is 0. So lambda to the 0 is 1, so you could really consider this as times lambda to the 0 or 1 equals 0. But we really don't need to consider that or write that out in our auxiliary polynomial. So the auxiliary polynomial then we form directly by looking at the the orders of the derivatives in the original differential equation and convert those orders into powers for the auxiliary polynomial. Okay. So let's take a look at a specific example. In this next example, and actually for the next 10 or 15 minutes or so, we're going to consider different types of solutions that we can get from the auxiliary polynomial. The first type of solution that I'd like to consider is the case where the solutions to the auxiliary equation are real and distinct. Now, the auxiliary equation is a polynomial equation. That lambda squared minus 1 equals 0 is a polynomial equation, and the solutions to a polynomial equation are called roots, to bring up a term from our pre-calculus. So let's consider, as our next example, the differential equation, our next differential equation, y double prime minus 3y prime minus 10y equals 0. Okay, so the order of the differential equation is 2, and that second order corresponds to the second power in the auxiliary equation. So we're looking at lambda squared minus 3. The first derivative corresponds to the first power, and the 0 derivative, which is gives us the original function, corresponds to lambda to the 0, or just the constant 10 equals 0. All right, so this is a polynomial equation. More specifically, it's a quadratic equation, and this one can be factored really easily. So let's solve this quadratic. Okay, if we factor the quadratic, we get lambda minus 5 times lambda plus 2 equals 0. So the two roots of our auxiliary equation are lambda equals 5 and lambda equals negative 2. These roots definitely have a specific structure. They're both real and they're distinct. So in this case, the roots of the auxiliary equation, p of lambda equals 0, are both real, and they're different from one another, so we say that they're distinct. Okay, so what we'd like to do is complete the solution to this differential equation, and then make a general statement about the solution to differential equations that have real and distinct roots to their auxiliary equation. Okay. So the solutions that the fundamental set for the solutions. Let me see if I can go back to my original color pen. The fundamental set for our solution is e to the 5x and e to the minus 2x. This forms a fundamental set. It forms a fundamental set of solutions because these two functions are linearly independent, and they're linearly independent because they're not proportional. So again, we're heading toward a theorem that's going to allow us to not have to state that the functions are in fact linearly independent. For now, let's just write our solution. So this is a fundamental set, of solutions. So the general solution is y equals c1 e to the 5x plus c2 e to the negative 2x. Okay. All right, now so let's take a look at a theorem that's going to allow us to not have to go through, for each of these problems, making an independent statement or determining that somehow that our the solutions to the auxiliary equation correspond to linearly independent solutions. In our textbook, this is called Theorem 4.6. So let's take a look at Theorem 4.6. Theorem 4.6 says that if we have distinct and real and distinct roots, so if R1, R2, all the way up to R sub k are distinct, remember that means different from one another, are distinct real roots of the auxiliary equation of P lambda equals 0, then the corresponding set of functions e to the r1x, e to the r2x, all the way up to e to the r sub k of x are in fact linearly independent. And now remember last time I said, or in our last video segment, I said that this course is for engineering and physics majors or science or STEM students. So that being the case, we really don't need to worry about a proof of this. So I'm not going to test you on the proof of this idea. It does though, this theorem does though allow us to go directly from the roots of the auxiliary equation to the general solution. Okay, so let's take a look at solving another specific example. So for example, let's solve the differential equation y triple prime plus y double prime minus 6y prime equals 0. In fact, I'd like to consider this as an initial value problem. So let's solve this with initial conditions y of 0 equals 4, y prime of 0 equals negative 17, and y double prime at 0 equals 11. Okay, so not only do we need to solve the differential equation, we need to find the constants in the differential equation that correspond to our three initial conditions. Okay, so first let's solve the differential equation. So first, solve the differential equation. And our method so far says that to solve a differential equation, you write out the auxiliary equation. So our auxiliary equation looks like lambda cubed corresponding to y cubed plus lambda y triple prime plus lambda squared corresponding to y double prime minus 6 lambda to the first corresponding to y prime equals 0. And again, we have another polynomial equation, and let's solve the polynomial equation. This one's not so hard because there's no constant term on the left-hand side. So we're going to factor out a greatest common factor of lambda. So lambda times lambda squared plus lambda minus 6 equals 0. Let's continue to factor this. So lambda times lambda minus 2 times lambda plus 3, I believe. Yeah, it looks like it works out. So we have the three solutions: lambda equals 0, lambda equals 2, and lambda equals negative 3. So immediately we go to the solution. So the general solution, is y equals c1 e to the 0x corresponding to lambda equals 0 plus c1 e to the 2x plus c2 e to the negative 3x. Now clearly we don't need to leave the first part of the solution as e to the 0x, since e to the 0 is 1. our solution then is C1, plus, I'll go back and fix the constants, C2 e to the 2x plus C3 e to the negative 3x. And I'm going to kind of go back up here. Right, the solutions, the constants is C1, C2, and C3 in the general solution. Okay, so our particular solution, though, is going to be the solution that corresponds to these three initial conditions. The three initial conditions are that the function goes through the point 0, 4, the derivative at 0 is negative 17, and the second derivative at 0 is 11. So let's apply the initial conditions. In order to do that, we're going to need, from our general solution, a couple of derivatives. So from our general solution, let's take a couple of derivatives. So our first derivative, the derivative of constant C1 is 0. The derivative of C2 e to the 2x is 2 C2 e to the 2x by the chain rule, 2x. The derivative of C3 e to the negative x is minus 3C3 e to the negative 3x. Okay, so let's take another derivative. Our second derivative then is 4C2 e to the 2x plus 9C3 e to the negative 3x. All right, so the way we're going to get our specific constants from the three initial conditions is to substitute the function back into the differential equation and solve for the constants. So now let's solve for the constants C1, C2, and C3 by applying our initial conditions to the solution. So our first initial condition is that y of 0 equals 4. So I'm going to take y of 0 equals 4 and substitute it into our solution. So this says that 4 should equal C1 plus C2 plus C3 by substituting x equals 0 into the right-hand side of y and setting that value equal to 1. We also have that the derivative at 0 needs to equal negative 17. So negative 17 should equal our first derivative when x equals 0. So this says that negative 17 should equal 2C2 e to the 2x minus 3, oops, oh my goodness. So now let's apply our second initial condition to our differential equation. So our second initial condition says that y prime of 0 should equal negative 17. And if we apply that to y prime, that means that negative 17 should equal 2C2 e to the 0, which is 1, minus 3C3. And finally, applying our third initial condition, y double prime of 0 equals 11 to our solution. So substituting y prime equals 0 equals 11 into our second derivative, we get 11 then equals 4C2 plus 9C3. Substituting x x equals 0 and to the right-hand side again. So what this results in is a system of equations, a system of 3 equations and 3 unknowns. And we've developed a whole bunch of ways of solving this. I used the Gauss-Jordan elimination method and found that the solution was, there was a unique solution. C1 equals 5, C2 equals -4, and C3 equals 3. So the only thing left to do then is to state our general solution. So our general solution to our differential equation is y equals C1 is 5, plus C2 e to the 2x, so minus 4 e to the 2x, plus C3 e to the minus 3x, so plus 3 e to the minus 3x. So now let's move on to the next case of roots of our characteristic equation, when specifically the characteristic equation has real repeated roots. Okay, so now we're looking at a characteristic equation, with real repeated roots. All right. So let's look at an example to see how this plays out. So for example, consider the differential equation y double prime minus 4y prime plus 4y equals 0. And let's construct the auxiliary equation. The auxiliary equation then will be lambda squared minus 4 lambda plus 4 equals 0. And let's solve this. So if we factor, we get lambda minus 2 times lambda minus 2 equals 0, or lambda minus 2 squared equals 0. So what this says is that lambda equals 2 is the only root of this quadratic equation, but this is considered a double root. If you recall from pre-calculus, we have a repeated root. So this is a repeated root, or a root of multiplicity 2. Okay, remember from pre-calc that every nth degree polynomial has exactly n roots or zeros, including multiplicity. So our polynomial factors into lambda minus 2 times lambda minus 2. So in fact, lambda equals 2 is a root twice, or it's a repeated root. So what we get is, in this case, only one of our two linearly independent solutions. We need another one. We need a second linearly independent solution. The second linearly independent solution can't be e to the 2x, because e to the 2x is not linearly independent with e to the 2x. They're proportional. In fact, they're equal. So what we're going to do is we're going to construct a second linearly independent solution. Okay, so what we do is, or what we need is, we need a linearly independent y2. That means, or that is, we need y2 such that y2 and y1 are not proportional. So y2 is not a constant multiple of y1. Okay, so this is what it means for two functions, y1 and y2, to not be proportional, or equivalently to be linearly independent. So if this is true, then we need y2 over y1 to not equal a constant. So we're looking for a second linearly independent solution such that y2 over y1 is not equal to a constant. So this is where we make a bit of a jump. Not too big of a jump. So if y2 over y1 is not constant, then y2 over y1 should equal some function of x that's not constant. So our goal is to find that function, let's say u of x, so that we can solve for y2 and get y2 is equal to u of x y1. So this is basically, how we're going to find our second linearly independent solution. All right, so our second linearly independent solution is going to have the form y2 equals u times y1. Okay, but y1 for our particular differential equation is e to the 2x. So our second linearly independent solution is going to be some function of xu times e to the 2x, our first linearly independent solution. So our job is to take y2, substitute it into the differential equation, and somehow from that solve for the second linearly independent, or rather the u of x, which will help us to find our second linearly independent solution. So let's take y2 and substitute it into our differential equation. What I've done here is to eliminate the of x and the u of x so that when we take our derivatives, that we keep the writing down to a minimum. So in order to substitute y2 into our differential equation, we're going to need two derivatives. So let's take a first derivative. y2 prime equals, now u is not a constant. Remember, u is some non-constant function of x. So in order to take the derivative of this function, u e to the 2x, we need to use the product rule. So the product rule says the derivative of the first, u prime times the second, plus the first times the derivative of the second, 2e to the 2x by the chain rule, or u prime e to the 2x plus 2u e to the 2x, or if we factor the e to the 2x out on the right side, we get u prime plus 2u e to the 2x. So there's our first derivative of our second linearly independent solution. So we have a second. So we're going to need a second derivative of our second linearly independent solution y2 to substitute into our differential equation. So let's take a second derivative. Again, using the product rule, the derivative of the first, y double prime plus 2 u double prime plus 2u prime times the second, e to the 2x, plus the first function, u prime plus 2u, times the derivative of the second function, 2e to the 2x. Okay, so simplifying, we get u double prime plus 2u prime, e to the 2x, plus, and maybe bring in the 2u prime plus 4u times e to the 2x. Finally, factor out the e to the 2x, u double prime plus 4u prime plus 4u times e to the 2x. And now we substitute the original y sub 2 prime, and y sub 2 double prime into the differential equation and figure out what u should look like, what this differential equation tells us that the non-constant u should look like. So the left-hand side of our differential equation with u2 substituted in looks like u2 double prime minus 4u2 prime plus 4u2, and substituting we get u2 double prime, u double prime plus 4u prime plus 4u times e to the 2x, minus 4u2 prime, so minus 4 times u2 prime, u prime plus 2u e to the 2x, and finally plus 4u2. So plus 4u2 is u e to the 2x. So factoring out the e to the 2x, we get u double prime plus 4u prime plus 4u from y2 double prime, and then from y2 prime, the y2 prime term, we get minus 4u prime minus 8u, and then also from the 4u2 term, we get plus 4u all times e to the 2x. And that's the left-hand side of the differential equation. The right-hand side of the differential equation, 0. So let's simplify. Let's simplify and move forward. This tells us that u double prime, we have 4u prime minus 4u prime. We have 4u plus 4u is 8u, minus 8u is 0. So we're looking at u prime. We're looking at u prime times e to the 2x equals 0. All right, now don't lose track of what we're doing here. We're looking for a non-constant function u to create or to help create our second linearly independent solution for the differential equation. So this this final equation is itself a differential equation, and let's solve for u. So since e to the 2x is never 0, u double prime must be. And this second order differential equation is of the easiest to solve if we integrate. If we integrate twice, we get u should equal sum ax plus b. If we integrate once, we get a constant a. If we integrate again, we get a constant ax plus a new constant b. Now keep in mind that this u is part of our second linearly independent solution that we're searching for. So if we were to substitute u into the form for our second linearly independent solution, we get u equals ax plus b times e to the 2x. However, we're looking for the simplest possible second linearly independent solution. The temptation might be to let a equal 0 and b equal 1, but that would produce e to the 2x, our original first solution. So the better thing to do would be to let a equal 1 and b equal 0 to simply get u2 equals the simplest possible second linearly independent solution will be x e to the 2x. Now we went through a lot of work to get that second linearly independent solution. The general solution then, the general solution is y equals c1 y1 plus c2 y2, or y equals c1 e to the 2x plus c2 x e to the 2x. And as mentioned just about a minute ago, we went through a lot of work to find y2. We won't have to go through this every time. What I wanted you to see is how that second linearly independent solution comes about. And it comes about by substituting, by forming the second linearly independent solution involving an unknown function u, and then finding out that u, in fact, the simplest possible value of u is x. The most important thing I'd like you to realize, though, is that if we have a repeated solution to our auxiliary equation, simplicity 2, then the fundamental set of solutions takes on the form e to the 2x, and the modifying e to the 2x just simply by multiplying it by x, so an x e to the 2x. This is generally the case. This works in general. So what we have to take us off the hook from having to do this every single time we have a repeated root is theorem 4.8 in your textbook. So theorem 4.8. Theorem 4.8. Theorem 4.8 tells us how to do this, or suggests how we should do this in general. Theorem 4.8 says that explicitly, if lambda equals r is a root of, let's say, multiplicity m, as in Mary, multiplicity m, then linearly independent solutions to our differential equation are e to the rx, x e to the rx, and this is where it would have ended if our multiplicity was 2, x squared e to the rx, if the multiplicity were 3, x cubed e to the rx, if the multiplicity were 4, up to x to the m minus 1 e to the rx, if our multiplicity is m. Okay, so basically to find linearly independent functions, if we have a root of a particular multiplicity, we do the following. So here's a final example to finish off this case. So for example, let's say, suppose we were solving a differential equation and we found our auxiliary polynomial to equal lambda plus 2 cubed. Okay, so in this case, lambda equals -2 is a root of our auxiliary or equation of multiplicity. Let's see if I spelled it right. Multiplicity 3. So our general solution is very easy to construct. It's y equals c1 e to the minus 2x plus c2x e to the -2x plus c3 x squared, one less than the number of our multiplicity, x squared e to the minus 2x. Okay. So let's finish our section by considering characteristic equations with complex roots. And if we do that, we've covered every possible type of roots that we can have for a polynomial equation. We started out with real roots that were distinct. Then we just looked at real roots that were repeated. And again, now let's take a look at the characteristic equation with complex roots. So the characteristic equation now is what we're going to consider to finish up our section. Characteristic equation with complex roots. Complex roots. Remember, complex numbers are numbers of the form a plus bi. In order to do this, we're going to need a formula that occurs really often in physics and engineering that you may have seen. I might have shown it to you in another application. In case we didn't look at it though, we have a formula. It's called Euler's formula. It's not so much important that you remember the name, but the formula is important. So it says that e to the I theta equals cosine theta plus I times the sine of theta. It's a really remarkable fact that this is the connection between the exponential function and the sine and cosine function, where of course I is the imaginary unit, the square root of -1. Okay, so if given Euler's formula, e to the I theta equals cosine theta plus I sine theta, suppose we have something like e to the complex number, e to the a plus bi. E to the a plus bi, let's even make this a little more suggestive here. E to the a plus bix then should be e to the ax times e to the I bx, just using rules for exponents. But Euler's formula tells us how to deal with the complex portion of this, the e to the I bx, and that says that this equals e to the ax times cosine bx plus I times the sine of bx. Okay, so this is basically the identity we're going to need. We're going to need the identity that says that e to the a plus bix equals e to the ax times cosine bx plus I times the sine of bx. So let's highlight that in blue. Okay. So, well, let's keep it highlighted in blue. So, with that in mind, let's take a look at our next example. So, our next example is to consider the differential equation y double prime minus 4y prime plus 5y equals 0. The auxiliary equation then becomes lambda squared minus 4 lambda plus 5 equals 0. This quadratic equation doesn't factor very easily, so what we'll do is we'll use the quadratic formula. The quadratic formula says that lambda equals the negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Okay, this gives us 4 plus or minus the square root of negative 4 over 2, or 4 plus or minus 2i over 2, or 2 plus or minus I. So from our previous discussion, this tells us that the two solutions that we get initially look like y1 equals e to the 2 plus I x, and y2 equals e to the 2 minus ix. And this is actually true. These are two linearly independent solutions. However, we'd like our solutions to be real valued. So what we're going to do is apply the blue formula above. The blue formula above that says e to the a plus bix equals e to the ax times cosine bx plus I times the sine of bx. to each expression. So this becomes e to the 2x times cosine x plus I times the sine of x. And y2 then becomes e to the 2x times cosine of negative x plus I times the sine of negative x. All right, so let's tear these solutions apart a little bit. This says if we distribute the e to the 2x, we get e to the 2x cosine x plus I times e to the 2x sine x. y2 then takes on the form e to the 2x cosine of negative x plus, let's move down here, times e to the 2x sine of negative x. Okay, this expression for y2 can be simplified a little bit. Cosine is an even function, so the cosine of negative x equals the cosine of positive x. So we get e to the 2x cosine x. Sine is odd, so the sine of negative x is negative sine of x. Sine of x. So it looks like we got these two really long, involved, complex valued, linearly independent solutions. But I want to look a little more carefully at them. Notice that in each of the functions, in each of the solutions, we have the repetitions of a couple things. So in the first y1, we have an e to the 2x cosine 2x, and in y2, we have the same e to the 2x cosine x. Okay. Let's see, that didn't work. Let's see if it'll work now. It's not letting me highlight. All right, well, I guess it's not going to let me do it then. Okay, so I won't highlight. So notice that in the first solution, we have e to the 2x cosine x. In the second solution, we have e to the 2x cosine of x. Also in the first solution, we have e to the 2x sine of x. And again, in the second solution, we're looking at our linear combination, having e to the 2x sine of x again. So rather than considering these two rather long, complex valued solutions, we can combine the two ideas into just yanking out the e to the 2x cosine x and the e to the 2x sine of x to get our general solution as C1 times the first of the two kind of repeated expressions, cosine e to the 2x cosine of x, plus another constant C2 e to the 2x sine of x. Okay, again, we're looking for real valued solutions, so we just yanked out the pieces of each of the y1 and y2 that were complex valued and formed a linear combination with C1 and C2 as the scalars of two linearly independent solutions. E to the 2x cosine of x and e to the 2x sine of x are clearly linearly independent. Those functions do not vary by a constant. They are not proportional. Okay, so let's summarize this problem again. We found that the roots of the characteristic equation P of lambda equals 0 were 2 plus or minus I. From this, we got our solution of e to the 2x cosine of x and e to the 2x sine of x. So if you'll allow me to, I'll insert a 1 as the imaginary part of the roots. The 1 corresponds to, back in the solution, the coefficients of x and the cosine and sine, and the 2 corresponds to the coefficient of x in the exponential portion of the solution. So if this didn't make sense, I want to summarize this generally. A couple of things happen here. One is that complex roots occur in what are called conjugate pairs. Conjugate pairs. The conjugate of 2 plus I is 2 minus I. Remember from algebra that the conjugate of a complex number a plus bi is a minus bi. And this situation always occurs if you have complex roots. They always occur in conjugate pairs. The most important thing is that if we know the conjugate pair, a conjugate pair of roots, then we automatically get two linearly independent solutions from them. So if r equal, let's do it this way. I think we're not using r. If lambda equals a plus or minus bi are roots of p of lambda equals 0, then e to the ax cosine bx and e to the ax sine bx are linearly independent solutions. If you're still any bit confused, this is really a very simple result to use in practice. So example, let's say consider y double prime plus omega squared y equals 0, where we'll assume that omega is some positive number. This isn't so important for us. The nature of omega is not terribly important for us. So let's solve this differential equation. The differential equation then, or the auxiliary equation then, is lambda squared plus omega squared equals 0. Careful, it's not lambda squared plus omega squared lambda. It would be omega squared lambda if it were y prime as opposed to y. That's a fairly common mistake that happens. The solution to this differential equation, or this auxiliary equation, comes about by subtracting omega squared from both sides and taking square roots. So lambda equals plus or minus I omega. So the theory above, or the statement above, says that our general solution is immediate. General solution is then y equals, well, if it's not clear, it may not be clear, so I'm going to add a 0 real part to our lambda. So the a is 0, so e to the 0 is 1, so we get cosine omega x, c1, plus c2 times the sine of omega x. Okay. Let's do one more to end this section altogether. So for example, consider the differential equation. Let's say the fourth derivative of y plus 6 times the second derivative of y, 6 times y double prime, plus 9y equals 0. The auxiliary equation is lambda the fourth plus 6 lambda squared plus 9, remember not 9 lambda, 9 equals 0. This factors very nicely into lambda squared plus 3 squared equals 0. So lambda squared equals negative 3. So lambda equals plus or minus 3i. But each of these roots is a root of multiplicity 2 because of the squared term right here. So each root is of multiplicity 2. Okay, so what I'm going to do to finish this off is I'm going to use a couple parts of our theory. First, because we have complex roots and they're purely imaginary, so the real parts are 0, so we don't get an e to the term, our general solution then is c1 cosine 3x plus c2 times the sine of 3x. And this would have ended it if we didn't have that extra exponent of 2 wrapped in red ink here. But since each of the roots is of multiplicity 2, we use the idea that we had before, and we multiply each of the linearly independent solutions by x to get additional linearly independent solutions. So this is plus c3 x cosine 3x plus c4 x sine 3x. And that ends section 4.2. And I'm looking forward to seeing you all next time.